Okay, so one type of problem we'll see here in terms of equilibrium is Q, where we're trying to decide if the system is at equilibrium, and if it's not, which direction it's going to shift. We can kind of break every other problem in the whole field of equilibrium into a second category, and that would be a category where something is missing. So in order to calculate Q, we need all the concentrations and we need the equilibrium constant to compare it to. The other types of calculations we'll look at, we're either trying to determine the value of K, or we're trying to determine what the concentrations of some of the components are at equilibrium, or determine something that stems from that. Like in the next chapter, we'll see the pH of the solution will stem from the concentration at equilibrium of a certain component. So the first example here is to determine K. And we'll see these problems all have some similarities as well that we'll get to as we go along. So we make a solution here by dissolving a certain quantity of moles of the reactant, diiodocyclopentane or cyclohexane, in a particular solvent. Solvent's kind of irrelevant here, it's just the concentration that we're going to need. Total solution volume is 1 liter. That's helpful. That means how many moles are dissolved will also be the molarity, since we divide by 1 liter to change that to molarity. Now, the other thing that we're told here is at equilibrium, the concentration of iodine, which is one of the products, is 0.035 molar. And we're asked calculate the concentrations of the other two components at equilibrium, beside the one that was already given, and to calculate the value of K. Now, if something is missing, so if the problem is not Q, we are always going to want to do what is called an ice chart. So we're going to want to take our equation, so I'm just going to rewrite the equation here so it's close to my chart, C6H10 and I2. And an ice chart looks like this. We have ICE running down in a column here on the side of the reaction. I stands for the initial conditions in our system, C stands for the change to those conditions, and then E stands for what happens at equilibrium. If something is missing, either K or concentration, we can use this chart to get the information we need to try to figure out how to proceed to getting that answer. So in this case, I want to fill in the data that I have, or what was provided in the problem. So I know initially my solution had a concentration of 0.050 molar in the diiodocyclohexane that I started with. Now, initially, that's before this reaction has even happened. There wouldn't be any products of the reaction, so those would be 0. Now, the other piece of information that I have here is that the concentration of I2 at equilibrium is 0.035 molar. Now, that gives me some information. If I start at 0 iodine and I end up at 0.035, that means the change to the concentration of iodine was 0.035 molar. Right? Now, that helps me because iodine and the product here, C6H10, they come from the same source. They come from decomposition of this original compound. So if this decomposed in a manner that formed 0.035 molar solution of I2, that would have to be the same change for the other product of the reaction, just from the stoichiometry of the reaction. And that means at equilibrium, it would also have a concentration of 0.035 molar. Right? Now, both of those, C6H10 and I2, come from decomposition of the reactant. So if the concentration of C6H10 and I2 went up by 0.035 molar, the concentration of the reactant must have gone down by that same quantity, since it's a 1-to-1-to-1 stoichiometry in the reaction. So if I start at 0.050 molar, but I know my concentration is going to go down by 0.035 molar, by the time I get to equilibrium, my concentration would be 0.015 molar for my reactant. Right? And there's the two answers we wanted for part A, concentration of C6H10I2 and the concentration of C6H10. The only thing we would still need to do here is calculate the equilibrium constant, K. Now, since we have a reaction, we know the equilibrium constant expression here. K is going to be the products, so C6H10 and I2. That was supposed to be a square bracket. Divided by the concentration of the reactants, just the one reactant here, no exponents because they're all 1, right? And now that we have those concentrations, we can just plug those in. So that would be 0.035 times 0.035 divided by 0.015 for diiodocyclohexane. And if we punch these in, 0.035 times 0.035 divided by 0.015, we get 0. And again, it looks like two significant figures here, 0.082 for our equilibrium constant. And I don't think I've said this yet, and it's certainly worth pointing out. Equilibrium constants don't carry any units. And the reason is really because it would be different depending on the reaction. You have several quantities of molarity or several quantities of atmospheres of pressure in that system, and so you'd get different units all the time, and the units don't really help for anything. So the answer here would just be 0.082 for this equilibrium constant expression. Now, the second problem here is a little different because we're given the equilibrium constant. So what we're looking for here are some of the concentrations, but we're still going to get there by using our ice chart and figuring out how we can make an equation that we can solve for whatever's missing. So given the equilibrium constant is 33, for this reaction, hydrogen gas, iodine gas gives 2 moles of hydrogen iodide gas. We're given the initial concentrations of the two reactants. We want to find what the concentrations are at equilibrium of all of the components. So again, ice chart is where we want to start. So I'm just going to rewrite my reaction here. Now these are all gases. I'm not carrying those phase indicators down here into my system. And if I go to fill out my ice chart here, initially it's a 6 times 10 to the minus third, that's 0.006 and 0.006, and that's already in concentration, already moles per liter, so we don't have to worry about the volume there for that one. And initially there wouldn't be any product in the system. Now, we weren't given, like the previous problem, we weren't given anything about what's the concentration at equilibrium. So we don't know what the concentration at equilibrium is here. That's where we're going to have to use sort of an unknown. We do know the stoichiometry of the reaction, though. So this reaction is going to have to shift forward because we obviously can't have a 0 at equilibrium. That would mess up any equilibrium constant expression we have. A 0 in the numerator would mean K would be 0. And a 0 in the denominator would be an unsolvable fraction. So we can't have a 0 when we get to equilibrium. And that means we're going to react some of the hydrogen. So I'm just going to call that X. Some of the hydrogen is going to react. Its concentration is going to go down by X. That means some of the iodine is going to react. Its concentration is going to go down by X. And when those hydrogen and iodine molecules react, they're going to be forming hydrogen iodide. And that means its concentration is going to go up by 2x. Now, watch the stoichiometric coefficients. For every hydrogen that reacts, we can get 2 moles of hydrogen iodide. Every mole of hydrogen that reacts, 2 moles of hydrogen iodide. So those stoichiometric relationships have to carry through your ice chart. Now, this would give us the ability at equilibrium to define all of the concentrations in terms of one variable, x. And that means if we have one equation with one variable, we, depending on the complexity, it's got x to the third in there. It might be hard to solve. But in this case, yes, we can solve this equation. Now, the equation is going to come from our equilibrium constant expression. So based on this reaction, we know the equilibrium constant expression would be concentration of the products divided by the concentrations of the reactants, right? And now that we have numbers and quantities in terms of x, we can just plug all those in. So 33 would equal 2x, but that whole quantity squared over 0.006 minus x times 0.006 minus x. Now, one thing to notice here, right, particularly if your algebra maybe is a little rusty, since the components on the bottom are the same, that would really be 0.006 minus x squared. So this is a squared term, this is a squared term. that means we could take the square root of all three pieces here, and this equality would still balance. That will allow us to get rid of the x squared term in this particular case. So if we take the square root of 33, that would be 5.745. I take the square root of the top of this fraction, that would be 2x. I take the square root of the bottom, that would be 0.006 minus x. Right? And now I have a much easier equation to work with without the x squared term. Now, in the next example, we'll see what happens when we can't do that, and we have to solve with that x squared term in the equation. But this one is kind of set up so we don't need to do that. So we do need to solve for x, though. So if we start to multiply out this equation, I'll take what I have here in the denominator and multiply it by the 5.747 in the left side of the equation. So 0.006 times 5.747 is 0.0345. And then negative x times that would be minus 5.745x. And that's going to be equal to 2x. So I'll want to add 5.745x to each side. So I get my x terms on one side, my numerical terms on the other side. That would give me 0.0345 equal to 7.745 times x. Right, so now I just need to divide both sides by 7.745, and I'll have x on one side, and I'll have a numerical value on the other side. So 0.0345 divided by 7.745 is, so 4.45 times 10 to the minus third. And since this x was in different positions back here, we don't really have our final answer yet. But we do have a numerical value for x here. So we can take this x and combine it with what we have back over here in our equilibrium constant expression to get our concentrations. So the concentration of hydrogen is going to be the same as the concentration of the iodine. That's going to be 0.06 minus x. So 0.006 minus 4, I'm going to round that to 4.5 since we have two significant figures, would be 0.0015 molar, or 1.5 times 10 to the minus third molar. Either one is fine. And then the concentration of hydrogen iodide, right, is 2x. So if this is 4.5 times 10 to the minus third, that would be, well, at 4.45, if we multiply before we round, that would be 8.9 times 10 to the minus third. And that would be in molarity as well. So there would be our calculation. Now, what we still need to look at is what if we can't simplify our equation? That's what we'll do on the next page and the next video.